Hi, everybody. This is Mr. Folly, and welcome to the last part. So, let me pause. This is going to be a tough one because I'm doing it in my car and I'm calculatorless. So, I've got some serious issues here. We might have to go with some estimations here. Determine if a precipitate will form for the following solutions. In each case, justify your answer based on Q. So, remember, if Q is bigger than K, you get a precipitate. And that's it. So, a 500 milliliter solution of 0.025 molar lead nitrate is mixed with a 255 milliliter solution of 0.0045 molar solution of Na2CrO4. The KSP of PbCrO4 is this. So the first thing we have to do is find out the right molarity. So I'm going to do the precipitate we're making is PbCrO4. So I have got to find the molarity of this. So I've got to do M1V1 equals M2V2 because I'm pouring solutions together. So the original molarity is 0.025. The original volume is 500. I'm looking, oops, I need an equal sign. I'm looking for a new molarity. And my new volume is, so my new volume is 255 plus 500. So 755. So notice you have to add those two volumes together. So then I can find out my new molarity. So I'm going to have 0.025 times 500 divided by 755, and that's going to be 0.0166 molar of Pb plus 2. Got to do the exact same thing for chromate. I have 0.0045 for my original molarity. My original volume is 255. Notice that, notice that my final volume will be the same. So let's see how we do on this one. 0.00, well, let me clear my calculator. 0.0045 times 255 divided by 755 is 0.00152 molar CrO4 negative 2. So then what we need to do is not look at new notifications. We got to write our Q expression. Q equals, so this is the dissolving equation for this. So it's just going to be Pb plus 2 times chromate minus 2. It's a 1-to-1 ratio. And now I've got to multiply those two together. So the number I had in my calculator times 0.066 is 0.1234. Wait, 1234. 1234252. And then KSP is 10 to the negative 15th, so Q is bigger than K. So precipitate. So 10 to the negative 13th, that's definitely not negative 13. All right. 255 milliliter solution of 0.015 cobalt nitrate. Not going to worry about nitrate. Is mixed with 150 milliliter solution of sodium hydroxide. Not going to worry about sodium. KSP for cobalt hydroxide is that. So again, we've got to do our M1V1 equals M2V2. Now, if, oops, I put VE. I must be excited for VE. Oop, but it won't erase it. There we go. So my original molarity is 0.015. Original volume is 255. New molarity. Volume is 255 plus 150. So 255 plus 150 is 405. So my new molarity is going to be 0.015 times 255 divided by 405. It's 0.009944 molar CO plus 2. So now I'm going to do the same thing. Might as well change the color because that's fun. don't think I did, though. I did. And then I need my OH negative. OH negative is original molarity is 0.0122. Original volume is 150 equals new molarity. New volume is 405. So my new molarity is 0.00944. And that's going to be OH negative. So now I need to write my Q expression, which is based on this guy right here. So I'm going to have two of them. So it's going to be CO plus 2 times hydroxide squared. So 0.00944 times, oops, why do I think that's the wrong one? 0.0122 times 150 divided by 405. It's 0.000412. What? 0.00452 molar. So that's going to be 0.00452 squared. So take that squared times 0.00944 equals 1, 2, 3, 4, 5, 6, 7. 1.93 E negative 7. And what is K? Still 10 to the negative 15th, which is bigger than K. So precipitate. Excuse me. In each of the following situations, determine the concentration of moles per liter of the anion needed to precipitate out the solid. So when we do this, this is where we're going to say Q equals K, and that's where precipitate happens. So we're going to say a bit more than, okay? So I'm going to start with K equals Ag positive times Cl negative. So K is 1.8 E negative 10 equals Ag positive 0.05. And I'm going to solve for Cl negative. Okay, so let's see if I can do this in my garbage calculator that I have here. So can I do that? I don't know that I can. So that means I got to do it with all the decimal points. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 8 divided by 0.05 equals 1, 2, 3, 4, 5, 6, 7, 8, 9. And there you go. Oh, stay there, molarity. Okay, so how many moles of NaI are needed to form AgI precipitate out of the total? There we go. So same deal. Okay, so how many moles of NaI are needed for? Okay, so we're not changing the volume, so we don't have to worry about dilutions. And I'm going to write the K expression for AgI. KSP equals Ag positive times I negative. KSP is, oh, that's huge, 8.3 E negative 17. And then Ag positive is 1.5 E negative 4. And then we'll solve for I negative, which is particularly hard with my really bad calculator. But we'll see what we can get here. So 8.3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 8, 3 divided by 0.12315 equals 0. Okay, so no, that's it. So I equals whatever your calculator tells you, because I am stumped on that one with a calculator without scientific notation. So boo, boo. Sorry. Explain how the image above illustrates an increase in entropy. disorder increases when ionic compound separates. So that could be an increase in the number of particles, more ways to arrange things, and so on and so forth. The Erlenmeyer flask above is allowed to sit on a lab bench such that all of the water evaporates. Oh no! What would happen to the aqueous ions in solution? They would precipitate out because Q would increase, right? So why would Q increase? Because the concentrations would go up. Explain why this process would result in decrease in enthalpy. Ionic compounds are more ordered than aqueous solutions. All right. Cadmium fluoride yields cadmium plus 2 plus 2F negative. A saturated solution of cadmium fluoride is prepared. Equilibrium in the solution is represented above. In the solution, cadmium equals this much and F equals this much. Determine the solubility of cadmium fluoride. So we're looking to find the molar solubility. So what that means is equilibrium solution is represented above. Okay, so we've got a saturated solution prepared, different ions, determine the solubility. So what I'm going to do first, I'm going to find KSP. KSP is going to be cadmium plus 2 times F negative squared. So cadmium plus 2 is 0.0585. Whoops, that sure looks like 885. 0.0585 times 0.117 squared. Okay, so let's see what my terrible calculator can do with this one. So 0.0585 times 0.117 squared equals, so my KSP equals 0.000801. Okay, so that's KSP. Then I'm going to do just like I would have done before. Cadmium fluoride equilibrium with cadmium plus 2 plus 2F negative. Sum 0, 0 minus X plus 2X. Don't care. X and 2X. Okay, I'm trying to block this off. So KSP equals X times 2X squared. So my KSP is 0.123801 equals 4x cubed. Uh-oh, I have a feeling I don't have a cube root in my calculator. Let's see what I can do here. Do I have a cube root? I do have a cube root. So 3 cube root. Uh-oh, I got to divide by 4 first. So I have 0.123801 divided by 4 equals, and then so 0.00, so x cubed equals 0.123200. So now I need to cube root that. So 3 weird cube root button. Oh, I just have a cube root button. Who knew? 0.000200 cube root. 0.0584. And that's the molar solubility. That's pretty high. Is the solubility of AgCl? So is the solubility of AgCl greater in distilled water or in tap water where the Cl negative is 0.01 molar? Justify your answer based on Q. So Q is Ag positive times Cl negative. And if I increase Cl negative, I increase Q. So that means it precipitates better. So solubility goes down because it's more likely to precipitate. All right. Solubility of cover is to be measured in 4 different solutions: distilled water, NaBr solution, and NaNO3 solution, and a CuNO3 solution. Determine the solubility of cover will be greater than, less than, or the same. Justify your answer based on the LTHS principle. Okay, so cover is what I'm looking at. And what if I'm looking at NaBr solution? So I'm going to add Br, negative. So more ions shift toward precipitate to, I'm going to say due to extra collisions. We'll go with that. Now I know it says using Le Chatelier's principle, but that's the shift towards the precipitate part. So I gotta make sure I answer this question. The solubility will be greater, so that means the solubility will go down. NaNO3, Na and NO3 do nothing. That would have no effects. CuNO3, nitrate, does nothing. You're adding Cu plus 2, so extra Cu plus 2 shifts away from plus 2. Not from plus 2, but from Cu plus 2, due to extra collisions. You could do the same thing with Q, but I asked for Chatelier, so I suppose we're going for collisions this time. A solution of silver nitrate reacts with a lump of zinc as shown in the reaction below. Lump, lump, lump. Give the net ionic reaction for it. So goodbye nitrates, goodbye nitrates. So I have Ag positive plus zinc yields zinc plus 2 because I'm getting rid of the ions plus Ag. I do need these 2's here to balance the charges. See how the 2 charges have to balance? What are the spectator ions? My old friend nitrate. Does the mass of zinc increase, decrease, remain the same as the reaction proceeds? Zinc decreases. Explain your reasoning. Zinc solid turns into zinc plus 2 in solution. So zinc solids mass goes down. The reaction between aqueous barium chloride and aqueous silver sodium sulfate forms a precipitate of barium sulfate. Give the net ionic reaction. Okay, so aqueous barium chloride. So if it's aqueous, it's going to be Ba plus 2 plus Cl negative. I can't get rid of anything yet. And aqueous sodium, goodbye sodium, but sulfate will remain. Forms a precipitate of barium sulfate. BaSO4. Tells us it's a precipitate, it's a solid. Chloride is doing nothing, so that's it. I'm all done. Toodles. Oh, wait, there's more. Oh, I thought I was Toodles, but I was not Toodles. All right, here we go. Use the figure above to answer the question that follow. Give the balanced equation for the reaction. So I've got Q plus N2, it's diatomic, will give me, this little beastie, Q2N2. Is that a balanced equation? No, now it's a balanced equation. Okay, determine the limiting reactant. Justify your answer by referring to the particles. Okay, so I have leftover black dots. So the limiting reactant is double ring, which is N2, because it's all gone. Assuming that all reactants and products are gases, would you expect the pressure of the container to increase, decrease, or remain the same? Explain your reasoning. Pressure would go down. You have 3 moles of gas, turns into 1 mole of gas. Would you expect Q to be a metal or a non-metal? Explain your reasoning. It's a non-metal because it's a gas and it's diatomic. For the solutions below 25, circle whether they have a high concentration of H positive or a high concentration of OH negative. Solution with a low pH has a high H positive. Solution with a high pH has a high OH negative. Solution with a pH of 10.2, remember 7 is the big divider. So a solution with a pH of 1.3, that's low, and that's neutral. Determine if the solubility would increase, decrease, remain the same for the following solids placed in the solution indicated. Would the solubility of CuOH taken twice increase, decrease, remain the same for the solution given below? In each case, explain your reasoning. Relative equations are given below. So notice here, low pH means lots of H positive. So OH negative is removed. And solubility increases. If you remove a product, it will shift it to the right. High pH, lots of OH negative. By the way, lots of H positive also means low OH negative. Lots of OH negative. So reaction shifts to the left-hand side and solubility goes down. Okay. With the solubility of FeCO3 increase, decrease, remain the same as solutions given below. In each case, explain your reasoning. Relevant equations are given below. So low pH, remember low pH means lots of H positive. So lots of H positive would removes CO3 negative 2. So solubility increases. If you remove CO3 negative 2, it'll shift to replace it. High pH means lots of OH negative. Let's see, what does that mean? Lots of OH negative would remove Fe plus 2. See how this OH negative and this Fe plus 2 would remove it? So solubility increases when you remove one of the ions. All right. With the solubility of CaF2 increase, decrease, remain the same in the solutions given below. In each case, explain your reasoning. Relevant equations are given below. So low pH means lots of H positive. Lots of H positive means it's going to remove F negative. A high pH means lots of OH negative. Lots of OH negative means it's going to remove Ca plus 2. Oh, I gotta actually say increase solubility. Increase solubility. All right. So these aren't really review questions. This came from a part of my source that has a different one. So 3 mole sample of CO and a 3 mole sample of H2O are introduced into an evacuated 1 liter rigid container where the temperature is held constant as the reaction proceeds. Give the equilibrium expression. K equals CO2 times H2 over CO and H2O. Equilibrium expression, so I'm given Kc, not Kp. Assume the mixture is allowed to reach equilibrium. How does CO2 compare to CO? Justify your answer referring to the equilibrium constant. K is large, so lots of CO2 product. Determine the equilibrium concentration of H2. Oh man, do I have to? I guess I do. CO plus H2O is in equilibrium with CO2 plus H2. Let's see, what did they give us? 3 moles of reactants only in a 1 liter container. So I'm going to call it 3 molar. I'm going to label it molar. 0, 0, minus x plus x, 3 minus x, 3 minus x, x, and x. My K expression would be x squared over 3 minus x quantity squared. K is given to me up here, 1.5 E negative, 1.5 E positive 3 equals x squared over 3 minus x squared. You heard me complain I'm calculatorless. I'd solver that and get an answer in molarity, which would equal CO2 and equal H2. The Kc and Kp in the reaction are the same. Explain why. all are gases. After reaching equilibrium, oops, I put my is on there. After reaching equilibrium, CO2 is added to the reaction mixture. In which direction must the reaction shift in order to reestablish equilibrium? The left-hand side. Whoops. Ooh. Okay. The reaction shown above occurs in an enclosed clear glass ampule. I love the ampule. The Kc for the reaction 35 is 12.5. What color is the ampule at equilibrium? Explain your reasoning. It's not clear. It's going to be light brown, not dark brown, light brown, because it's mostly products, but a little bit, remember I was going to have a little bit, few brown reactants are there. The temperature is increased and the ampule turns dark brown. Is the reaction exothermic or endothermic? So if it was exothermic, and if I increase the temperature, it would shift to the left. Hey, that would work, right? It's exothermic because if heat is on the right, adding heat shifts to the brown left-hand side. I almost forgot my F. All right. Does the K increase, decrease, or remain the same? So if it's shifting to the left, K would decrease. Oh, how did I know that was going to move with it? And I believe I halfway tootled it the first time. Oh, man, another? Okay, 52. At 450, the value of Kc is 50. Determine the concentration of HI will increase, decrease, remain the same under the following conditions as the system progresses towards equilibrium. Explain your reasoning by discussing the relationship between Q and K. Okay. Well, H2 increase, decrease, or remain the same, and talk about what happens between K. At 450, the K is 50, so it's 50, so it's big. So it's going to heavily favor the products. Will the concentration of H2 increase, decrease under the following conditions as the system progresses towards equilibrium? Oh, I got to solve for K, for Q. Okay, so K is high squared over H2 I2. So that's going to be 1 squared over 1 times 1. That's going to be 1. So Q is less than K. So what's the question? Determine if the concentration of H2 will decrease. So H2 will go down because it's going to shift to the right-hand side. Here we go again. K equals 4. I'm going to go ahead and put this in my quick. 4 squared is 16. Uh-oh. 0.005 squared is beyond my mental math. 0.005 times 0.005 equals 2, 4. So 16 divided by 0.123425 is 640,000. K equals 640,000. So that's going to shift to the left-hand side. So H2 will go up. In this one, I'm going to have 2 squared over 0.05 over 1.6. So let's see here. 4 divided by 0.05 divided by 1.6 is 50. No shift. Q equals K. Oh, I said K is 640. This would be Q is 640,000. AG I is in equilibrium with AG positive plus I negative. K equals AG positive bracket, I negative bracket. CaF2 equilibrium. Ca plus 2F minus. K equals Ca plus 2 bracket, F minus bracket squared. CuBr, equilibrium arrow. Cu plus 1 plus Br minus 1 K equals Cu plus 1 bracket. Br minus bracket. Mg OH taken twice. Equilibrium. Mg plus 2 OH negatives. I'm going to put it over here. K equals Mg plus 2 OH negative squared. CdCO3 equilibrium arrow, Cd plus 2 plus CO3 minus 2, K equals Cd plus 2 bracket, CO3 minus 2 bracket. Oh. Ooh. Solid ALOH has a KSP of 1.8 E negative 5. Determine the OH negative in the saturated solution. So I'm going to do this a shortcut way. KSP equals, I got 3 of them here, 27x cubed times x. So 1.8 E negative 5 equals 27x to the 4th. Let's see how I do on my terrible calculator with this. So I've got to do, let's see here, 1.8. Oh, I can't do scientific notation. Oh, I can. Oh my goodness, I just found it. 1.8 EE negative. Oops, that's not gonna work. 1.8 EE5 plus from. Oh, that's not gonna work either. 1.8 EE5. Oh no. Okay, so I can't trust it at all. So 1.81234 divided by 27 equals. So x to the 4th equals 6,666. That sounds kind of demonic to me. So let's see if I can 4th root that bad boy. 4th root. 6,666.1. That doesn't seem right to me. So x is going to be determine the OH negative in concentrate. So whatever that is, x to the 4th. Oops, x equals something. Come on. X equals something. And then 3x is going to equal hydroxide. Determine the pH of the saturated solution. So 3x, so negative log of 3x is going to equal POH. 14 minus POH equals pH. Determine the Al plus 3 dissolved in 50 milliliters of the solution, the mass. So that's going to be X, right? So X is going to be the molarity of Al plus 3. So then moles equals molarity times volume. So moles are going to equal whatever this number is, right? So I'm going to call that X, right? It's this X. Times 0.05. And then that will give you an answer in moles. So then that answer in moles equals that. So then that answer in moles times 1 mole on the bottom, and then 26.98. The mass does not change because of a charge, because electrons weigh squat. Determine the molar solubility in moles of this. So again, whatever X is. Man, it stinks not have your calculator, doesn't it? Yep. Lead to arsenate is a slightly soluble solid. A saturated solution has lead with this concentration. Determine the KSP of lead arsenate. You know what? I think you can't do this because it could be other things. So I'm actually going to call this review stuff that's enough. Just because it's 34 minutes, I don't have a calculator and I'm frustrated. So I will say to this, check the printed thing that'll actually have numbers on it that'll be posted on Canvas. Toodles.